Alrighty, looking here, section 2, inductive and deductive reasoning. All right, so last section, we talked about, well, we ended with truth tables and truth values, right? Is something true, is something false? Can it imply something true, something false? Um, Up here, we talked about different statements that we have, right? We have a conditional statement, and then from the conditional statement, there's three follow-up statements: the converse, the inverse, and the contrapositive. So those are all just statements, but what if we string some different statements together? We're going to be thinking about, are we using inductive or deductive reasoning, right? And that's kind of like just doing observations, but then we have the law of detachment and the law of syllogism, which really talks about putting things together or different statements going together, especially law of syllogism is really talking about putting multiple statements together. Let's read here. A conjecture is an unproven statement that is based on an observation. All right, let me read that again. A conjecture is an unproven statement that is based on observations. Okay, so you see something happening and you say, hey, look at this. This is happening. You use inductive reasoning when you generalize from past observations. So think about a pattern. All right, so the example that I give is that you have a friend, and the friend wears shorts every day. They don't like to wear pants, they like to wear shorts. Okay, so you're sitting in class with your friend. Your friend is wearing shorts, and they've worn shorts like every day. You can make a conjecture that tomorrow, when you see your friend, they're going to wear shorts, right? I don't know if you talk with your friends about whether or not you wear shorts or pants, but there you are. You've got a conjecture. You're probably going to wear shorts tomorrow. And you are even using inductive reasoning there because you're generalizing from the past. In the past, you've seen them wear shorts, so you're going to make a conjecture that in the future they're going to wear shorts, right? That is using inductive reasoning. You're looking at something into the future, from past to the future. All right. Deductive reasoning uses facts, definitions, and accepted properties and laws of logic to form a logical argument. This is different from inductive reasoning. All right. Conjectures and inductive reasoning, those are all just talking about like factoids, things that you see. Okay. Deductive reasoning has to be much more solid, much more concrete. Deductive reasoning is talking like, for us, we're talking about maths. You'd say, well, x equals 5, so 2x equals 10, right? You can say that. You can show me that. You can show me that with proof, with hard proof. So a true conditional statement means that P implies Q is true. We talked a little bit about that in the last section. And then lastly, the laws of logic. So we've got two of them. Law of detachment. Let's read this. If the hypothesis of a true conditional statement is true, then the conclusion is also true. Okay, so that's talking about the up here, right here. So they're saying that if this thing is true, so if we have the true, and the true, we throw out this falsehood, we throw him out. Then it's saying that if true, then true. Well, if true, then true. Or let me circle that one. If true, then true. There we are. Okay. Law of detachment talks about a statement, a conditional statement, and you think about, well, is the conditional statement true? And then what can you conclude from that? The law of syllogism talks about putting statements together. So you start off with if P, then Q, then Q, then R. Right? So you have two different statements. Well, they're saying you start off with if P, then Q, then you can jump over to here, Q, then R. You can kind of put them together. Well, if P, then R. Right? So it's like putting two different statements together to make a more simple statement. So example 8 here. This one here is going to be us kind of using a conjecture and using inductive reasoning, right? So you think about the problem where you're, not problem, but the situation where you're telling your friend, hey, you're going to wear shorts tomorrow, aren't you? Because you've worn shorts every day. So here we're looking at these pictures and we're going to generalize from the pictures. Figure 1, 2, 3, and 4. And we can probably see what's happening. They're adding on these last boxes, right? And this one they added on these boxes. So what is it? There's 4 tall. So our next one is going to be 5 tall. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. All right, my picture isn't perfect, but that's what it would look like, right? It would have 5 and 5 because we were seeing that they were adding 1 on each side. Okay, that is using inductive reasoning. Okay, you don't know for sure. It might be that figure 5 does something. It might be a star. Like you don't know, but you're just saying you're going to pull from the experience that you have, and the experience that you have is just looking at these 4 examples, and you're going to generalize to get the new one. All right, number 9, make and test a conjecture about the product of a negative integer and a positive integer. All right, so we want to make some kind of conjecture. Okay, so I'm going to say product of negative and positive is positive. You probably read that and you say, well, that's going to be false. Well, that's okay. It didn't say to make a true conjecture. It just said to test it. There's my conjecture. The product of a negative and a positive is a positive. Well, and now I'm going to test it. Well, some negative number, negative 5, times some positive number, 3. What is negative 5 times 3? That's negative 15. And we know that this guy is false. All right, that's all we have. Conjectures don't have to be true. They're just conjectures. Okay, and then even if this was true, that's not proving my conjecture. That's just saying, well, here's a situation where it works out, right? We have to do a little bit more math later on. We'll be able to do that, where we're actually able to like rigorously prove whether something is true or not. All right, let's look at example 10. A student makes the following conjecture about absolute values. Find a counterexample to disprove the student's conjecture. All right, so someone else made a conjecture, and we're right now telling them, no, you're wrong, and here's why you're wrong. The absolute value of the sum of 2 numbers is equal to the sum of the 2 numbers. All right, so let's think about this. We have this piece and then this piece. So the absolute value of the sum of 2 numbers, so I'm just going to pick out 2 numbers, negative 3 plus 2. So we've got negative 3 and 2. They're saying it's equal to just the plain old sum, negative 3 plus 2. Well, good grief. This was actually going to work out for us. We're going to have negative 1 equal, oh, nope, it's not. Negative, absolute value of negative 1 equals negative 1. That's 1 equals negative 1. That is not true. So we say that was false. That's it. Okay, we're just trying to say, is your conjecture true based off this, or is it false? For something to be false, you only need one counterexample, right? Kind of like what I was talking about with example 9. You only have to find one time where it doesn't work. But for it to be true, you have to really take a lot of time to show that it's true, and it's true all the time. All right, number 11. If a quadrilateral is a square, then it is a rectangle. You know that quadrilateral ABC is a square. Using the law of detachment, what statements can you make? Well, law of detachment just means you can kind of plug in to a statement. So we have this conditional statement here. It's an if-then. We have the if. It is a square. It is a square. So we can jump over and say, well, it's a rectangle. We could say A, B, C, D is rectangle, or is a rectangle. Okay, that's using the law of detachment, right? You're just kind of plug it in and you're going, okay? Now, next up, example 12. If possible, use the law of syllogism. Now, remember, the law of syllogism was when you take two separate conditional statements and you build them into one bigger statement. Well, it doesn't necessarily mean bigger, but it spans over both of the original ones. So let's look here. We have if soccer practice is canceled, there's Q. You go to the mall after school. That's P. So you start off with Q, then you go to P, and then we have this other statement. If it is raining today, I don't know, we'll make that R. then soccer practice is canceled. We'll make that, we've already got soccer practice canceled listed. It is Q. All right, so we have two statements. We have Q implies P, that's our first one. And then we have R implies Q. That was from our second one. And I think it's really beneficial to actually list out little variables here for our statements. And we can see here that we've got Q repeated. So we can say R to Q, Q to P. Kind of like that. And then we don't normally write it like that. We end up saying R implies P. Oops, if I could write correctly, that'd be nice. R implies P. Now I want to actually write this out. So I'm going to say if it is raining today, then what's P? What was P? You can go to the mall, right? If it's raining, soccer's canceled. If soccer's canceled, you go to the mall. So we can say, then you can go to the mall today. Then you can go to the mall today. There we go. All right, let's look at our next one. If a figure is a rectangle, then all angles in the interior of the figure are right angles, okay? If a figure is a square, then all angles in the interior of the figure are right angles. Well, that's great. We've got two different statements. But let's think here. We've got P implies Q, and then we have some other things. The square, that's R, implies Q again. We can't write it like this. We can't do something like that, where it has like a double arrow. We can't do that, so we can't really say anything about this. There's nothing fancy we can say. Now, well, let me stop. There's things we could say, but we can't use the law of syllogism to say it, okay? So, if possible, not possible. There we go. That's our answer. All right. What conclusions can you make about the sum of two even integers? And then it says to prove it, right? And I've got those little air quotes there because this is going to be kind of a simple proof for us. Well, what happens to two, what is this, product? No, sum. Well, it's the sum of two even numbers. Well, it's going to be even. It will be even. So to prove it, we have two numbers. And I'm going to say we have 2m and 2n. Now, the reason that I'm writing that is that anytime you have an even number, he has a factor that's 2, right? So rather than saying that m is an even number, I'm saying m is just some number, any number at all. I don't care what number it is. But if you take him and multiply by 2, now he has to be even, okay? So we'll say, I don't know, they said integers, so we'll say m and n are integers. So m and n are integers, and then by listing them as 2m and 2n, they have to be even. Now, they say we're going to, what do they say, sum, right? That means adding them. So I'm going to say, well, 2m plus 2n, right? I'm going to add them up. Now, remember, I'm trying to show that this is even. So I'm going to factor out a 2. And right here, I've got this 2 hanging out front. I have no idea what m plus n is. I don't know what it is. But if you multiply it by 2, that's an even number. So there we are. That's it. That's our little bitty mini proof, right? We're not trying to be any fancy. We're just trying to show it right there. All right, so let me write this down. 2 times an integer, integer is an even number, right? I'm writing that factoid down for us. All right, let's look at our next one. Decide whether inductive reasoning or deductive reasoning is used for each statement. Then explain. If the sum of the digits of a whole number is divisible by 3, then the number is divisible by 3. The sum of the digits of 147 is 12. So 147 is divisible by 3. That is going to be deductive reasoning, because it used the laws of logic. It used conditional statements. It used laws of logic. Okay, and what law of logic was that? I think we can even say that would have been the law of detachment, wouldn't it have? Because we kind of plugged in for that formula there. All right, next up. Each time you forget to do your math homework, your parents take away your phone privileges for a day. So the next time you forget to do your math homework, your parents will take away your phone privileges. Well, that's kind of like your friend wearing their shorts every day, right? You're just saying, well, maybe in the future, you're probably going to do it. You know, it doesn't say here. It might have been that the parents outright said, hey, this is the rule. Now, if that was the case, if they had this hard, fast rule, then you could have used deductive reasoning. But they didn't say that they had that rule. So this is going to be inductive. Because based off what is given, we're just observing a pattern. Observing a pattern. No rule, right? There's no rule listed. We're just observing a pattern. All right, there we are. That is section 2. Let me scroll back up and see what's the important things we want to make sure we know. Really, it's these words up here. We're going to need to know the word conjecture, inductive reasoning, deductive reasoning, a true conditional statement, which is just I would read that backward. It's a conditional statement that's true, right? We've already talked about that. The laws of logic, that's a rule, or that's a term that we should know. And then law of attachment, law of syllogism. Those are all good things that we need to know. All right, that is section 2.